Hello, this is Mrs. Kim, and I'm here with Mr. Knox and Mrs. Erling. This video is about Chapter 8, Sections 2 and 3. Section 2 starts on page 272 and ends on 277, and Section 3 starts on 279 and ends on 282. There are two ways you can express the age of a rock or the fossil inside the rock. One is with its relative age, which is just comparing which one's older or younger, and the absolute age, which is the actual number of years since the rock has formed. So I would like you to pause this video and look at this picture of the family and give the relative and absolute age of each of the members. Okay, did you do that? Okay, so then you might say, Father is 45 years old, Grandma is 67 years old, and Jane is 3 years old, and that would be the absolute age. And if you said Grandpa is older than Dad, that would be relative age. Or if Mom is older than the daughter, but younger than the grandma, that would also be relative age. The law of superposition says that when you look at a sedimentary rock layer, you can see all these different layers. The layer at the top is the youngest, and as you go deeper and deeper, each layer is older and older, and the oldest layer at the bottom. When you make a sandwich, you put the bread down on the plate first, then you might put ham, lettuce, cheese, and then you would put the final bread on the top. And the one on the top is the youngest, the most recent. Scientists look at igneous rocks when they want to determine the relative age of a rock. If they see an extrusion, which is lava that hardens on the outside of the earth, think of the word exit or the prefix X, that means outside. So extrusion is lava that hardens on the Earth's surface. You know that the rock was there before and then the extrusion covered it, so you know that the extrusion is younger. Intrusion is when lava hardens below the Earth's surface, and think of the prefix in or inside, and they are also younger than the rock that it cuts through.
We can use clues from faults to determine the relative age. A fault is a break in Earth's crust, and forces inside Earth cause these rocks to move, and you can see the fault right here. So a fault is always younger than the rock that it cuts through, and we can find the relative age of a fault by comparing it to the youngest rock layer. So a fault must be younger than the youngest layer of rock because the fault happened after the rock was fully formed. There are gaps in the geologic record where some layers are incomplete. They may have eroded, exposing older layers underneath. And scientists study the layers and patterns of erosion to help determine a relative age. So we call these gaps in the geologic record an unconformity, and this is where new rock layers meet a much older rock, and we're missing the rock in the middle. We also use index fossils to date rocks. Index fossils are widely distributed, meaning you can find them in a lot of different places. They are a type of organism that only existed briefly, and in a geologic sense, a couple million years is considered brief. They help tell the relative age of the rock layers in which they occur. So in the picture over here, we have ammonites, which are used as an index fossil. These ammonites were found near Greece, and their dark coloring indicates that they come from very deep in the ocean. These ammonites, they were hard-shelled animals, and they only lived a couple million years. Table talk. So if you found the trilobite fossil on the left here in a rock, how old would that rock be? Well, pause the video, look at the geologic time scale below, and try to figure it out. Hopefully you paused and figured it out. So if we look down towards the bottom of the geologic time scale, we can find the trilobite right here in the Cambrian time period, about 100 million years ago.
So now that you learned about relative dating, we're going to figure out how to get the exact age of a rock. And to do this, we use radioactive dating. And as the name suggests, radioactive dating entails radiation, which is chemistry. So I'm going to try to do a little chemistry unit as quickly as I can so you guys can understand radioactive dating. Well, all matter, that's everything in the universe, is made up of atoms, and atoms are really, really small, much smaller than a cell. If you Google scale of the universe 2, it's a really cool website that shows you how big and small things are. So pause the video, go to Google scale of the universe. It's well worth it. We're going to show that in class as well. So atoms. Atoms of a similar type make up an element. Now, some elements are what we call radioactive, and radioactive elements are very unstable. They give off radiation, and this radiation is usually in the form of heat, and as it gives off radiation, the radioactive element changes. So something like uranium would change into lead, and of course this takes a long period of time. So this is the backbone of radioactive dating. Now, to determine radioactive dating, we need to figure out exactly what element is being changed. Scientists can measure the radioactive element in a rock, okay? And the radioactive element, here we have the radioactive element, or the parent atom. Now, this is very unstable, and it slowly changes over time, giving off energy or giving off this particle. And nuclear power plants use this to create electricity. However, this parent atom, because it lost an electron or two, now is changed into a different atom. Now, this occurs slowly. And if you look at this picture, this is a great representation of how it occurs. At first, you have this parent atom, and it's 100% radioactive and very unstable, like most parents. But over time, this parent slowly starts to degrade, and there's more and more daughter cells, which happens in real life too. You know, as the daughter grows up, the parents slowly disappear and, you know, dissolve away into nothing. But that's a different story. Anyway, so we have this parent atom right here. We have lots of it, and then slowly over time, half of it disintegrates, then half of that disintegrates, and then half of that disintegrates. Now, if there was a way that we could figure out the half-life of elements, or half-life of these radioactive elements, we could determine the age of rocks. And in this next slide, it shows different half-lives. Here we have uranium, which will eventually change into lead. Now, how long does this take? Well, its half-life takes 4.5 billion years. That's with a B. So, in order for uranium, for half of the uranium to go from this to half of it, that's 4.5 billion years. So uranium degrades very, very slowly. If we look at another example here, carbon-14. Carbon-14 is a radioactive element that'll change to nitrogen-14. That only takes about 5,700 years for one half-life. So for carbon-14 to change, to a half-life. That's 5,700 years, 5,700 years, 5,700 years. So radioactive elements or radioactive dating gives scientists a very good idea of how old a rock was, or how old a rock is, I should say. So two ways to determine the age of rocks. There's relative dating, and then there's what's called radioactive dating or absolute dating.
Remember, relative dating is not going to the movies and pizza with your cousin.
All right.